Section 3.4, Modes of Digital Communication. I'm Dr. Rico Piccone. This is a section from the book Real-Time Computing for Mechanical Engineers, published by MIT Press. Check it out at their website. And also at the companion website for the book, rtcbook.org. Modes of Digital Communication. Digital communication systems generally follow the architecture described in Section 3.1 with the 3 layers. However, there are many variations in the implementation of the architecture for different types of communication systems. The reason why there are differences is that different applications and environments call for different specifications. For instance, long-distance transmission over cables is much different than short-range wireless communication. However, if every product with a communication system had its own methods, the wheel would constantly be reinvented. Shared channels, for example, the radio spectrum, would be in disarray, and infrastructure would be unnecessarily duplicated. For these reasons, communication standards have been developed and widely adopted. Before turning in the next section to look at some standards of particular interest for real-time computing, we review 3 important modes of digital communication: serial parallel, synchronous asynchronous, and simplex duplex. Standards are usually described in part in terms of these 3 divisions: serial and parallel communication. Communication over a channel can be serial or parallel, in the former taking place sequentially and the latter simultaneously, as shown in the figures. So in serial communication, we have a series of transmissions and receptions, and in parallel communication, we have simultaneous transmission and receptions. Serial communication transfers 1 bit of information at a time and has significant advantages for long-haul communication since the channel needs to have only a single path, for example, a coaxial cable, which have only 2 terminals at each end, the inner conductor and the outer conducting shield. So you don't need to have a bunch of wires. Parallel communication transfers multiple bits of information in parallel, which can be faster than serial communication but has disadvantages, such as requirements for synchronization and a channel with multiple paths. Serial communication speed has increased in recent decades, and it is frequently preferred even over short distances. This is possible, this advantage of serial communication, because serial channels with their single signal path do not have a specific problem that plagues parallel communication: skew. Skew is the difference in travel time that each path within a parallel channel can have, which is primarily a result of differences in path length. This isn't much of a problem for a cable with multiple conductors or paths, but on a printed circuit board, PCB, skew can be significant. Synchronous and asynchronous communication. Synchronous communication relies on a common external clock to time both transmission output and reception input. The clock, usually a digital signal itself, signifies when the signal at the receiver is valid and should therefore be read. Asynchronous communication does not use an external shared clock to tell the receiver when to read the incoming signal. For this to work, the transmitter and receiver have to agree on several aspects of the structure of a signal. Of particular interest in this chapter is asynchronous serial communication, which is the mode of communication used by a universal asynchronous receiver-transmitter, or UART, and many other communication protocols. A common problem for all protocols that use this method is how will the receiver know when information is coming? Consider that the receiver is just watching the incoming line, which can be at only one of 2 logical states, high or low. Each protocol has a default state, often called mark or idle state, which is of course either high or low. If the first bit or more in an incoming data stream happens to have the default state, the receiver would never know about them. For this reason, most asynchronous serial communication protocols use a start bit that has the state opposite of the default state. So if a line is by default high, the start bit is low, and vice versa. After the start bit, there are data bits, sometimes parity bits, and a stop bit. This is called a data frame for the communicated information. The transmitter and receiver must both work with the same data frame, something either fixed by a shared protocol or configured by some other means. At the end of the start bit, the receiver will wait some fixed duration t and treat the signal state at that moment as the first data bit, and the signal for the first n integer multiples of t as subsequent data bits. The size of n is commonly 8, a byte, but this is not always the case. The baud rate or bit rate is 1 over t, typically given in units of bits per second or BPS. The shared baud rate of transmitter and receiver is not synchronized with a shared clock, so the small differences between clocks can become problematic for large n, which is one of the reasons why n is kept small, for example, just 8. Sometimes the last bit or so of the data bits are used as parity bits for error detection by the channel decoder. There are two common forms that use a single parity bit, even and odd parity. In even parity, the transmitter sends a logical true 1 parity bit if the number of true 1 bits in the data is even, and a logical false 0 when it is odd. Odd parity has complementary logic, which lets the channel decoder check the parity of the received data. Of course, if an even number of bits are incorrect, checking the parity bit will not be sufficient for error detection. However, that can only happen when at least 2 bits have errors. If the probability of getting 1 error is 1%, the probability of 2 is around 0.01%. Usually, the probability of an error is much lower, but error correction is nevertheless important because many pieces of digital information come in large chunks. Even an email sans attachment can be 100 kilobytes or 800,000 bits. Finally, one or more stop bits follows the data bits and has the default state. Why do we need a stop bit if the number of data bits n is known by the receiver? The primary purpose of a stop bit is to ensure that the line returns to the default or mark state before a new start bit arrives. Note that a start bit can have a different duration than the data bits that follow. The vernacular around this can be confusing. Common start bits are called 1 bit, 1.5 bits, and 2 bits. What is signified by 1.5 and 2 bits here is the duration of the start bit. Okay, simplex and duplex communication. Communication systems can also be characterized in terms of the direction of data flow. In a simplex channel, data can flow in only a single direction, such as from node A to node B, as in the top figure. So, from A to B. In a half-duplex channel, data can flow both ways, but in only one direction at a time, as shown in the middle figure. So either from A to B or from B to A at a given time. Finally, in a full duplex channel, data can flow in both directions simultaneously, as illustrated in the bottom figure. So A to B and B to A, those communications can occur at the same time or not. In full duplex, you can have communication both ways at the same time. Okay, so that concludes these different modes of digital communication. We'll pick it up next time. See you then.